we say back here about the relationship between Pn and A star? If A minus Pn is less than A minus A star, then Pn must be bigger than A star. If Pn is bigger than A star, then the area of the big polygon that's inscribed is bigger than the circle in which it's inscribed. That's insane, right? Reductio ad insanitas. Absurd, okay? In other words, the big inscribed polygon, miraculously now, is greater than the area of the circle in which it's inscribed, because this ratio here is greater than 1. That's a huge contradiction. That's a no-no. Can't do that. Cannot happen. Okay? So you do the other case. That can't happen either. So what can happen? They have to be the same. Well, what has to be the same? For circles. For circles, that has to be the same, which is an amazing result considering the time, which is about 300 BC. Basically, the guy did a limit and showed that the assumption that areas of similar figures for round shapes work just like it did for rectilinear shapes was valid. It was an assumption up to that point. This is an actual proof based on a very transparent axiom. I think the Gaussian axiom is pretty easy to accept. You just keep hacking until he gets down below epsilon. Okay, stop. Finite number of steps. As long as you're willing to take away more than half at each shot, you're there. So that's good enough for today. You get the hang of this? So Rob's going to do the loop thing. Here's what I'd like everybody to look at. Anybody want to talk about figure 12 on page 7 and figure 13? What exactly is Archimedes doing? I have read elsewhere that this proof represents the absolute pinnacle of reasoning in Greek geometry. The so-called quadrature of a parabolic segment. It's a very clever theorem. You might be able to find another proof on the net. I'm having trouble following Burke's drawing here. Like I said, I can't figure out whether some of his drawings are a little obscure. But anyway, the idea is this. If you have a parabolic segment from here to here, and you connect the dots, right? And then you make a triangle anywhere inside. So you pick some sliding point here and complete the triangle. Then the area of the entire parabolic segment is exactly 4/3 the area of the triangle, and the Greeks can figure out the area of the triangle. It's an amazing thing, considering the resources that they had available at the time. I mean, he was probably drawing this in the sand with a stick.
We know what particularly works.
Conics, probably. I'll bet you.
I'm wondering if I have what is it, encyclopedia did a work called Great Books, and they have all kinds of authors, including Plato, but I think Archimedes is also
why don't you
well
see
as things like the paper 40 did on
Why don't you see if you can find proof of this? Okay. No, you can't, you can't.
I thought there was something like this on history. With a lot of stuff.
In Chuck's course?
Yeah.
Maybe you can find it.
Yeah, I stopped looking for it.
I have the book too, I can take the course.
Oh.
That's why.
Well, did it have? I mean, we've just reported the result here, but do they have a proof? Not a modern proof. I mean, I guess we can do this with calculus without too much trouble, but the idea is to sneak up on calculus. Use the resources that would have been available to the Greeks. Do that. Okay? All right. That's step one. So Rob's going to do something. You guys are going to do something. And then on page 9, I think I can do a power series proof of that argument that pi over 4 is the alternating odd harmonic series. Right? 1 minus a third plus a fifth minus a seventh. All that's equal to pi over 4. The alternating odd harmonic series is pi over 4. That's an arctan argument. So the integrated arctan. Sorry, 1 over 1 plus x squared to get arctan. So that arctan is 1. You set the variable equal to 1. Of course, arctan returns pi over 4, and then when you put 1 into the series terms, it returns the alternating odd harmonic series.
Is there any other math for that proof?
So what?
Is there any other math to
Apparently so. But here's what I'm stuck on in Burke's book here. You see about midway down page 9?
Yeah.
1/2 AB times OC is the area of AB. The triangle OAB. He really doesn't draw a triangle OAB. A and B are supposed to be points that are close together. Triangle OAB. Of course, the line from A to B is curved. It's not straight. But somehow that's supposed to be equal to the linear distance. I think he means the linear, not the curved distance from A to B. Times this damn line here, OC. It's a projection from a tangent. I'm not able to prove that yet. I'm looking at it, so why don't you guys see if you can see what the heck's going on, okay? So everybody has something to do until Thursday. And then Thursday we'll go the full 2 hours because you'll have read maybe all of one, and we'll discuss these issues, and then we'll start getting into the definition of the early integrals, the Cauchy and Riemann integrals, okay? There's a few that are left out. You guys, have you ever heard the name Darboux? Pardon? Well, the upper lower Darboux sums and upper lower Darboux integrals, if they're equal, you get the Riemann integral. It's a slightly cruder version of the Riemann integral, and we'll go through them. Okay?